All right. Okay, so next session before lunch, we've got 2 back-to-back lectures introducing you to stochastic simulation, the theory behind stochastic models, and how they relate to the models which we've already seen and have some experience of working with now. So every model, dynamic model, epidemic model we've looked at to date have taken the form of sets of differential equations, which we sometimes refer to as deterministic models. Okay, what do I mean by deterministic? I mean that every time we run the model from the same initial conditions, we'll get exactly the same answer coming out. That's a really nice, attractive feature to mathematicians because it means we can really study carefully and understand the behavior of these models. And we have lots of centuries of tools for analysis and understanding the behavior of such differential equation models. They're a really convenient starting place for mathematicians. And under certain limits, they have got a good enough description of a lot of different physical and biological processes, including the spread of epidemics. However, applying these types of models to biological populations has at its heart a little tiny screaming kernel of insanity. There's a sort of fundamental problem with using this type of model, and that is that differential equations work on real numbers that are changing continuously, whereas real populations involve individuals who do not typically decay away to turn into tiny little fractions of individuals. But that's something which happily happens in a differential equation model and isn't a realistic description of a real population. Populations are much more naturally represented by integers, whole numbers of individuals. And rather than changing at fractional rates, changes in populations occur due to discrete events. We need to have a birth event in order to get an extra duck in our population. In fact, if we only had one duck, we'd be rather surprised to find another duck. So there's a lot of biology which isn't captured by simple rate equations. Likewise, and perhaps most importantly, natural populations will suffer local and global extinctions. Okay, that is a natural part of what populations are, and it's something that just isn't described in any way in a deterministic model. So you'll have seen in the population models we've looked at, you can have tiny fractions of individuals in the population, tiny fractions of infectious individuals, but the disease never goes extinct, the population never goes extinct. The other aspect of real biological populations that these deterministic models, especially the well-mixed models, don't capture is the huge amount of variation that we see in real populations. So this is the time I stole this picture. This was the tallest woman in the world and the smallest man in the world, just as a cartoon illustrating the breadth of variation that we get in real populations. And for epidemic diseases, what's more important is the breadth of behaviors and possible interactions which can contribute to the spread of disease. You could take a philosophical view that these are all things that we could, in principle, measure, understand, and model. I would suggest that's a route to insanity. And actually, to a certain extent, the interactions within populations are intrinsically stochastic. There's an element of these interactions that are just unknowable, and we need to incorporate that variability and uncertainty into our models. At best, what we can measure from a real population is some form of average of the rate at which a process might happen. Okay, whether that's a birth rate, a death rate, a transmission rate. Yeah? These are all estimates which apply at the population level, yeah, whereas the mechanisms at the individual level will be subject to uncertainty. Okay? So we might be able to characterize on average when something happens, but we won't necessarily be able to say this is going to happen to you then. Okay? That uncertainty in the timing events and the ordering of events leads to a very special type of intrinsic stochasticity that we see in population level models. Okay. A bit of terminology, so just adding to our bestiary of terms so that we've been exposed to them, maybe confused. When talking about stochastic processes, a language which is often used is talking about the process, which people will refer to as the systematic or the deterministic changes. So we could almost think of these as the rates of our differential equation. There is some sort of process which is going on, but then there's also noise. There's random fluctuations on top of that. And there's lots of different types of noise which can feed into population dynamics. Okay? And this language comes from signal processing in physics, where you're interested in the process more than the noise. What's a bit different with biology is the noise is sometimes as important as the process, because the biology is in the noise. Okay? In these lectures, we're going to focus on a very particular type of noise, a very particular type of stochasticity, which is called demographic stochasticity. And this is that uncertainty in the timing that events happen, which are occurring at a constant rate. Okay? So this is, we're going to explore what happens if we have a model where processes occur at fixed rates, but the time between events actually happening is random. Another important source of noise in biological populations is what we term extra demographic stochasticity. It's sometimes called environmental stochasticity. Again, we've got a lot of terms here, but it's because different people use the different terms to refer essentially to the same thing. This can be thought of as variation in the rate that events occur. Okay? To understand what I mean by this, demographic stochasticity is a sort of intrinsic feature of our model, in that if we set up the mechanisms and processes in our model, then demographic stochasticity is what happens when we run the model or when the model is explored. It's an intrinsic factor of the model. So it's a bit like putting a kitten in a box. Okay? You put the kitten in the box and it bashes around and it creates some variation, okay, which is related to the properties of the box and the kitten. Extra demographic stochasticity is more about things changing, affecting the parameters of the model. Okay? So that's more like kicking your cat in the box. Okay? Sorry to people who like cats, they never like this example. But it's something extrinsic to the model, which is why we call it extra demographic stochasticity or environmental. This can be really important for pathogens that are transmitted through the environment or are affected by climatic variables. But we're not going, it's also an important source actually in terms of model fitting, because it can help us to account for the fact that our models are always wrong. If we allow for some variation in our parameters, it helps to account for that model error. But that's not what we're going to talk about today. We're going to be focusing on extra demographic stochasticity.
Sorry?
Yes.
So when
Or demographic.
When we were defining our deterministic model, did we at any point specify or fix the point the infection was happening?
We specified the rate at which transmissions occurred and the rate at which individuals and compartments recover or are lost or are input, but no. We were thinking about averages at a population level rather than individuals. And there is an explicit link between thinking from individuals and those population averages, which we'll talk about in the next lecture. Okay?
Yeah, I'm just trying to kind of make the link between what you said, like the change is happening within a compartment,
Yes.
right?
Yes.
That may be like when we run the simulation, when we are using, for instance, the deterministic model. When we run the simulation for the first time, then the infection is happening at a certain, like, let's say, time equal to 5, for instance. And then when we run again, it's still time equal to 5. But what you are saying is that something is happening so that when we run the simulation for the second time, for instance, the infection may not be happening at t equal 5, but at a different time.
Exactly. So in a stochastic model, we include that uncertainty and variation, which is averaged out in a deterministic model. And there is actually an explicit link, which, yeah, we'll describe. Okay, there's lots of different ways to build stochastic models. And again, it sometimes depends on your application. You might want to do it in discrete time. You might want to do it in continuous time. You might want to use what's called a Markov chain. You might want to have non-Markov events. These are all terms you don't understand yet. But as our starting point, I'm going to introduce you to what's called a continuous time Markov chain. And this is the most general and most accurate representation of a stochastic process. I will talk a little bit about the limitations and how we can account for that for epidemic models in the next lecture. Okay, but what are we going to do? We're going to describe our population now by integers, so that's whole numbers. We sometimes call these state variables. So this is like the compartments of our model in the deterministic framework, but state variables could be structured at the individual level. You could have an individual status, or we can just track in the same way as we do in deterministic models the numbers that are in different states. Our state variables will change now due to events rather than changing fractionally, and events will occur randomly according to fixed rates, which are probabilities per unit time. And this is how we will define and specify our stochastic model. Okay, so rather than writing down a set of differential equations, okay, well, our starting point really should be drawing our compartments to decide what our relevant states are and what the processes are. But instead of writing down differential equations, we will tabulate, make a table for all of the possible events that can happen in the model, the effect that it has, and the rate per unit time, the probability per unit time of those events happening. Okay? So for a simple birth, the effect is that the population size increases by 1, and the rate at which that happens is given by the birth rate, which here I've modeled as a per capita birth rate. Okay? So exactly the same terms that we use in our differential model will come into our stochastic model. We just use them in a different way. Okay. Fundamentally in this question, in this first lecture, I'm going to be asking the question what the impact is of demographic stochasticity, so this uncertainty in the ordering that events happen, has on population dynamics for a series of simple population dynamic models. Okay, and I'm going to start really simple with a constant births model. Okay, simplest possible population process, we only have one event, birth, and it's going to occur at a fixed probability per unit time. Okay? One state variable, which is the population size, and the probability of a birth occurring in a small interval of time, delta t, so that's the probability that n goes to n plus 1, will be approximately b times that small fraction of time, delta t. Okay? Does that make sense? Okay. If we were to write a deterministic ODE model for this birth process, we'd write it down as dm by dt equals the constant b. Okay? So what would be the solution to this differential equation? What type of population growth would we expect in this model? Linear, absolutely. It's a constant, so we integrate this, we get a constant times time, linear population growth. Okay, so here I have plotted the deterministic solution, which is this thick black line, and using a method that we will discuss next, I have simulated multiple realizations of the stochastic process. So the big difference with the stochastic model is every time we run it now, we get a different answer. We get a different type of population growth. So each of these colored lines is a different realization of the stochastic model. And what we can see is that they essentially fluctuate around the deterministic solution. Okay? That's because the deterministic solution is capturing the average behavior of the stochastic model. Okay? It's a very particular, and actually it's a new type of average than the ones we've talked about in the course before. We've talked about time averages when we were thinking of force of infection. We've talked about averages over age if we were talking about the mean age of first infection. This is what I've described here as an ensemble average. So it's an average over the different realizations or replicates of the stochastic model. Okay? So it's as if we're living in a, if we think of looking at multiple different parallel worlds, which all take a slightly different path, okay? We're averaging over all of those possibilities to get the average, okay? There's more information in the stochastic model because we also have this insight into the variability we would from the average. Yeah?
So how do you determine which iteration or you could choose, since some of them are below the average, some of them are above the average? If you wanted to choose one of the realizations.
Okay.
Yeah.
So if I was a dishonest man who wanted to get a science paper, I would choose the one that fits my data the best. Perfect. The real answer is you don't. The whole point is there is not one single trajectory. Yeah? So actually, if you're the whole point of simulating from a stochastic model is you're going to generate variation which is greater than you see in a particular realization. Okay? We have this fundamental problem in epidemiology that we have one world that we are experiencing, one epidemic even often that we're trying to understand. And when we go through, so your question is really important actually in terms of interpreting what happens when we fit a model. Yeah? So if we fit trajectory match a deterministic model, we are essentially fitting to the mean. Okay? If we fit a stochastic model, we're more or less doing the same thing actually, in that we're going to get variability about the mean, an envelope around the mean for our fitted model. Now, it may be that our data is actually an extreme, and there's no way of knowing that without having multiple replicate data, and that's a fundamental challenge that we have with epidemic data. There's ways of dealing with this, and I'm sure TJ will have a lot of opinions if you ask him about how you can constrain or condition your fitting based on the past history of the epidemic. Yeah? But for simulation, the entire point of using a stochastic model is that we don't just have one realization. So stochastic model is a lot more realistic. We're creating a huge amount of extra work for ourselves though, because we have to deal with not just one run of a model, but we have to commit to doing hundreds, thousands of replicates. But that gives us more insight into how unlikely or likely the particular set of observations we might have is. Okay? It's a good question, that's why I went off on one. Okay, so how did I make these simulations of the stochastic process? Okay? Before we do that, just want to remind ourselves of how we solve a deterministic model and how we make that deterministic trajectory. So we have seen already that we can essentially integrate or solve our differential equation model by just stepping forward in time by small steps, delta t, and updating the value of our state variable n to n plus the rate of change times the small step. Okay, so that's the Euler time step solution. Not how we do it in practice, but in principle, delta t is small enough, we can solve any differential equation like this. Okay. Difference with the stochastic model is that in our little small interval of time, the event may or it may not happen. Okay. We can calculate the probability that an event happens. We did that already. Okay. And then we can simulate, or we can sample from a distribution to decide whether or not an event has happened at a particular time. Okay? So as long as this delta t is small, there's a constant probability that something happens. Okay? So we can partition a line, okay, between 0 and 1, with 1 being something definitely happens, 0 doesn't. And then if we set a line on the probability of the event happening, and then we sample a random number, a uniform random number between 0 and 1, then if that random number is below the line, we do the event. If it's above the line, we don't do the event. Okay? And then we just keep iterating. Okay? So on average, the event will fire at the same rate as given by that we've used to specify the process. Okay? Does that make sense? Okay.
Which events are you talking about?
In this case, it's just birth. Yeah? So we've just got a birth event, which happens at rate beta, at rate b. Okay? So if we want to step for in a small interval of time, the probability that that event happens is b times delta t. Okay? If we sample a random number between 0 and 1, then if that number is less than this probability, we simulate. Okay? If it's greater, we don't. And then as we repeat over time, it will converge to the average of the event firing at the right rate. Okay? This is just a construction that we've used, which will give us the right number, the right rate of events that we've specified. Okay?
Just trying to understand. The event can be the infection, for instance.
It could be anything. Yeah? And we're just, so what I'm doing here, I'm building up the general algorithm that we'll use to simulate a full model. This is just thinking about if we have something happening at a constant rate. Yeah? How would we, on a computer, using random numbers, simulate the process? So as in the practical, where we simulated the roll of a dice yesterday, or die, rather, or simulated a fact there was a constant birth-death process, which is exactly the same as this. So we have a probability of death, and if we sample in this way, yeah, and look at the average of the number of times the event has fired, it will have the same rate as we sort of put in. Okay, so it's just an artificial way construction in order to get the right average rate of events happening.
So can you just try to make the difference between the deterministic model and the stochastic in terms of the rate of transmission or the force of infection, for instance? So what the deterministic model is doing and what is happening? Okay.
So in the deterministic model, yeah, we would take, as we step forward, we increase the value of n by a small fraction. Yeah? The size of that fraction depending on how big the time step is and the value of b. Okay? So we just go from 1 to 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7. Okay? In the stochastic model, in the stochastic algorithm, we have the same rate. Okay? But then in the first step, we maybe sample the number and nothing happens. So we go from 1 to 1 to 1 to 1 to 2. Yeah? And if we look over lots and lots of steps, the rate will be the same in terms of how often you flip up, but you only have the integer steps from 1 to 2 to 3. Is that okay? Yeah.
So it means that for the stochastic process, we introduce like variability in the rate,
No, the rate's constant, but the variability comes in when in the timing that the event happens. Okay? So in a small step, we know that there's a chance. So if you think of light bulbs, okay?
So
Every time you switch on a light, there's a chance it will blow, which is constant. Okay? If you look at 1,000 light bulbs, yeah, we could characterize by looking at how often they blow when you switch them on average, how likely they are. Yeah?
okay. So for the deterministic, it's more like the rate is constant,
Mm-hmm.
and it just happens.
And the population changes fractionally.
Okay.
Yeah?
But with this one, we would have to calculate like a probability of whether it happens or not.
It's the same probability, it's the same rate,
Okay.
yeah, but it's being used in a different way. Yeah? We're deciding, do we increase by 1 at this point? Is there a birth, or does nothing happen?
And what determines that?
We pick a random number on our computer. So we could toss a coin. Any source of randomness would be okay. Yeah? On a computer, on R, we'd use the uniform random number generator to generate a number which is uniformly distributed between 0 and 1. Okay? Which means, so if this is our probability of an event happening, this is 1 minus p. Yeah? So if we sample from a uniform random number, 1 minus p of the times, nothing will happen. And p of the times, we will decide to do an event. Okay?
So eventually, it will all converge to the point.
Well, no. As you can see, it diverges.
Yes.
Yes. But if we average over many different trajectories, we get the behavior of the deterministic. The deterministic is capturing that average. Yeah? But individual trajectories will actually continue to diverge and drift. Okay? Away from the center. Yeah? You can see it from the graph, but yeah. Yeah. Okay? Everyone happy?
I think I'll be happier with more examples as we go on.
Okay. Okay. I mean, this is the starting point. Is everyone happy about what a uniform random number is and how we generate that on a computer? You had a question as well. Sorry.
It was about the way you said for stochastic it can remain at a certain point, then it just
Yes.
goes back to the next
Yeah.
level of next time. So I'm wondering whether it's then appropriate to do stochastic when you have a very long time, because it might mislead in the when you are doing at a certain point, then maybe the next time it's supposed to jump to another level.
So, a few slides on, we're going to derive the time between events. We're going to show that we can actually derive what the time is between events. Okay? So this algorithm that I've described, it's called an explicit tau leap. It's an approximation. Okay? And really, it's a useful way for simulating some stochastic models, but it's not exact. Okay? Because we can actually do a bit better than this, and we can work out what the distribution is that describes the time between different events in a stochastic model. And that's the general purpose way that we simulate stochastic models. Now, as to whether or not, so if you have a long time between events, this would be a very inefficient way of simulating a stochastic model, but the exact method that I'm going to derive would be much more efficient. Whether or not a stochastic model is appropriate or not depends more on the size of the population. Okay, and we'll see that again later as we look at some more examples. Okay? So what we're doing here, what we're going to be using a computer to do is to simulate these random numbers in a computer. Does that worry anyone, given what computers are designed to do and how they work, that we're using a computer to generate random numbers. Is that concerning in any way?
Say what you said again.
So are computers a good device to make random numbers? No, they're terrible because they're designed to give you the same answer every time you do a calculation. That's what you want from a computer. Yeah? So what we do on computers to generate numbers that look random is we use special algorithms which generate numbers which have the same statistical, or streams of numbers that have the same statistical properties of random numbers, but are not actually random. Okay, so if you start them from what's called the same seed, they will produce exactly the same stream of numbers. Okay? But if you look at the average and the variance, it will be the same as you would expect from true random numbers. Okay? I used to have a couple of slides on this in the lectures, but I've dropped it out because actually computer technology's moved on a little bit, and most modern computers have got a little unit in them which has a little thermal sensor or a little quantum unit which generates true random numbers. So you can actually generate true random numbers on modern computers. It's a bit slower, but you can use that to generate a seed, which will effectively give you a true set of random numbers. For simulation and for model fitting, it almost doesn't matter, because sometimes you want to know the seed so that your work is reproducible. Sometimes you want to change the seed so that you make sure that you are actually, your model is actually robust and you've not just got very lucky in terms of the seed that you've chosen. But partly it's a clever trick, but the algorithms are good enough that we can treat the numbers that we get out of R as having the same properties as a true random number. Okay, we spent a lot of time on this slide. I think it's good you're engaging with it. Hopefully it's going to make everything a bit easier. So as I've said, this is a very slow way of simulating a stochastic process, and we can do a lot better. We can find what the probability distribution is that describes the time between events that are occurring at a constant rate. Okay? At this point, a lecturer's always got a choice. They either pull an equation out of the hat and say it can be shown, or they try and do a proof. This is one of the few cases where I try and do a proof, because I think it's a good one, and I think it's useful, and it's hopefully simple enough to follow. Okay? So, we're going to introduce some notation. We're going to let tau be the inter-event time. So that's the time between births happening. Okay? We want to derive the cumulative probability distribution for tau. Okay? And I'm going to define this as Q, the probability density that tau is less than a value t. Okay? So what are the properties of this probability density function? We did this yesterday. What properties does it have to have? So if it was a probability density function, it would have to have an area under the curve of 1, and it would have to be strictly greater than 0. Here we're going to derive the cumulative probability density function, which is the integral of the density. So it has to have a maximum value of 1, minimum value of 0. Okay? I'll show you why we want that cumulative function in a second. Okay? So the start of the proof is the worst part, because it's where we do something that seems weird, and then it makes sense why we've done it only at the end. So we're going to let P of tau be the probability that no event happens after tau units of time. Okay? It turns out it's easier to work with no events happening than working out when an event happens. If we do that, then we can write down from first principles what's the probability that no event happens in another small interval of time, delta t. Okay? So the probability of no event in tau plus delta t is the probability that nothing happens up to time t. Okay, so that's just the definition of that distribution. And the probability that nothing then happens during the next time step. Okay? Probability something happens is b times delta t. Probability nothing happens is the complement. Okay? So I just used the complement rule from yesterday and the and rule from yesterday, multiplying probabilities together. Okay? There was a reason for the broccoli. This is where we were aiming for. Okay. If we rearrange this equation, okay, and we take collector terms together so that we've got on this side p of tau plus delta tau minus p of tau, and then we bring across the other, the delta t over to this side, then put it in this form, okay, we have got minus b p of tau on this side, and then we've got this funny looking thing here, which should hopefully be familiar. What does that look like? It looks like the definition of a derivative, doesn't it? That's kind of handy, because if we take the limit as delta tau goes to 0, then we can identify that this is the derivative of p of tau with respect to tau, and it is equal to essentially a constant times the function itself. Okay? So from first principles, we can write down a differential equation that describes the probability distribution that we want. Okay? And it's also one that we know the solution to. What's the solution to this going to be? There's only one function, which is its own derivative.
The exponential.
Yes! The answer is always the exponential function in this course, pretty much. Love exponential functions. So p of tau is equal to e to the minus b tau with some constant that we're just going to gloss over for now. But we can choose the constant based on the normalization. Okay. Now remember, that isn't what we wanted to know. This is the probability that nothing happens. We want to know q of t, which is the complementary probability that an event happens within a time interval, and that's just 1 minus. Okay? So this is the inter-event time distribution for a general stochastic process which occurs at a constant rate. Okay? And the result is that the time between events will be exponentially distributed. Okay? So I am going to now take a risk and try and do some maths on the whiteboard. So why is it useful to have this complementary distribution? So let's just do a quick plot of it. And sorry, because my arm, I am doing this. This is going to look really bad, but my Q will be the wrong way around. Okay. So what is this graph going to look like? So at time equals 0, is it going to be, what value is it going to have? 1? So if we put tau equals 0 into this, we get e to the 0, which is 1, so it's 0. And then when tau goes to infinity, we're going to get 1. Okay, so it's going to have this shape. Yeah. Okay. All right, which is very typical of a cumulative probability distribution function. Okay. Why is this useful? So on the y-axis, we've got a number between 0 and 1, which maps uniquely to a value of the time to the next event, okay, to the random variable. Okay. If we want to simulate the time to an event, then we just need, again, to sample a random number between 0 and 1, and then map it back using this function to get a unique time. Okay? And we can actually turn around. So if we say this is a random number between 0 and 1, r, yeah, then r equals 1 minus e so minus b tau. We can solve this equation for tau and get an expression in terms of our random number. Okay? And if I was more mobile in my left hand, I'd go through all the steps, but I'm not. So you can show, if you take the time, that tau is minus 1 over b log, natural log of r. Okay? All right. Or equivalently, we can just use the REXP function in R for exactly the same result. Okay? We can either simulate using a uniform random number, or we can just get an exponentially distributed random number directly using the function in R. Okay. Given this result, we can now write down a more elegant and efficient way of simulating this simple birth process. Okay, and this is, we generate, so I've got side by side here, and actually that looks terrible on that board, so let's go back over here. That's a bit better. On the right-hand side, I've written down what I would call pseudocode. Okay, pseudocode is essentially describing in words what the algorithm is that we want to implement on the computer. Okay, which we could then do in any programming language that we want. We could do it by pen and paper if we want. Okay, so the algorithm to simulate the simple birth process, first of all, we generate a random number between 0 and 1. We use it to sample from the exponential distribution to give the time from the next event, delta t equals this. Okay? And the R code to do this is just a simple while loop. Okay? We start by setting up the population size, set the time to 0, set a maximum time, set the parameters, and here I have put in a little bit of extra code to make an interactive plot. Okay, so we make an empty plot, and then while t is less than t max, we update the time to the next event, update the state variable, and then plot the points. Okay, so what we get is this stepwise relationship between the points. Okay? All right. Let's try and make it a little bit more complicated. What if we have a per capita birth rate model? So instead of a constant birth rate, we have a birth rate that depends on the size of the population. Okay? So deterministic value model would look like this. dm by dt equals mu n. And the solution would be a exponential model. Yeah, of course it's an exponential. It's always an exponential. Yeah? Okay. There's no change here, actually. We can simulate this model, stochastic model, using exactly the same algorithm, because between each step of the model, the rate of events is constant. Okay? Although the rate of births is increasing as the population size increases, yeah? Between each step of the model, it's still a constant probability. So the time to the next event is exactly the same as before. Okay? So if we simulate, again, we see a very similar pattern where it's not as obvious now that the stochastic models are scattering around the average. If we put things on a log scale, it becomes a bit clearer. Okay, that again, we have the same process. We have the deterministic model is capturing the average, the ensemble average, across the stochastic replicates. Stochastic model has a lot more variation around that average. Okay. All right. If we want to generalize this algorithm to a more complicated model, we need to make use of something called the Markov property. So providing probability of events are time independent in our model, and determined only by the current state, okay, by which I mean the number of susceptibles, infected, recovered, the size of the population size, then we say that the model satisfies something called the memoryless condition. Oh, that's horrible notation, but it's a conditional probability definition. It's saying that the probability that of the model being in the next state only depends on the current state of the model and not on the past history of the model. Okay? It's easier, ignore the notation. So if we have a trajectory of the model, the memoryless condition says as long as the probability of this next event happening only depends on the values of the variables here and not on the past history, then we can develop a general purpose simulation algorithm which can be used for more complex models. Okay? Solid example. Let's say we look at logistic growth model, okay, that we've seen in the practicals and lectures already. So we have a per capita birth rate, but we have a nonlinear density-dependent death rate with a carrying capacity. There's a few different ways you could translate this into a stochastic model. Here we say that we've got a per capita birth rate, and then we have a nonlinear death rate. Okay? So now we have two possible events that can happen, which occur at two different rates, okay, but which depend only on the size of the population at each time. Okay? So at any time point, we can add up the rates and calculate the total rate, which will then determine the time to the next event happening. Okay? So to simulate a model with multiple different rates and processes going on, we just need to calculate the total rate and then decide which of the events happened. Okay? So there's a two-stage process to the simulation. Okay? So writing this out in words, in pseudocode, this is what's known as the stochastic simulation algorithm, the Gillespie method, or if you come from a different field, you might name it after another dead white male European, but it's the obvious thing you would do. You generate a random number, 0, 1, you use it to sample from an exponential distribution, the rate parameter now the total rate, and then we generate a second random number, okay? And we use it to select which event occurs next. And we do this by using a construction very similar to the one I used with the explicit tau leap. We have a number line where the total rate is at the end, and then we mark off where the rates are, and then depending on where a random number lands, we choose that event. Okay? So again, over time and over multiple replicates, we will be choosing either, in this case, the birth or the death at the correct rate as specified by the equations. Okay? Does that make sense? Okay, I'm not looking at this side of the room enough. I hope you're happy over here. If you're not, shout up. Okay. And yeah, we can do this just by, in our code, just by sampling from the R exponential function. Okay. So, stepping over here, now have some code which does the Gillespie algorithm. Okay, I've split it up a little bit more, just as an illustration of how we can you can use functions to make your code easier to understand and easier to read. Okay, so we've got the boilerplate at the top, which just sets up the parameters and the plot. We've got the inner main loop, which is a while loop again. And then I have written a function which calculates the rates of the logistic function. So it just returns a vector with the birth rate and the death rate. And then samples the time to the next event, summing the rate vector to get the total rate. And then another function which does the event. Okay, so this is doing that, partitioning the line. So we calculate the total rate, we get a random number. If x times the total rate is less than rate 1, then we do a birth. Otherwise, we do a death. Okay? So we can use these conditional statements, so again, that we learned about in programming, to decide which event happens based on a draw of a random number. Okay? So, very similar pattern here, in that we've got the deterministic model is capturing the average of the stochastic simulations. Okay? Few interesting differences. What's the most interesting difference with the stochastic version of this model?
At the beginning, it doesn't go above the average.
That's a really good point, actually. It's late. Yeah, the growth is slower on average than the deterministic model. There's a really subtle reason for that we'll come back to in the next lecture. But that's a really good point. There's another thing that's fundamentally different in the stochastic model. This side of the room, anyone? Stochastic model is doing something that will never happen in the deterministic model. I mean, most importantly, it's overshooting the carrying capacity. Yes, in the deterministic model, that carrying capacity is a hard limit. Population never goes above it. In a stochastic model, it will overshoot and then course correct, and we get these fluctuations around the carrying capacity. Okay? So stochasticity is a way to generate fluctuations and periodicity in populations. And that's something which would not be predicted by the deterministic model with constant rates. Okay, so we have a very variable, I've said, a variable delay time in reaching the carrying capacity. So there's a lot more variation in this early phase than there is in the later phase. And then we see these fluctuations around the carrying capacity, which wasn't in the deterministic model.
So, in effect, will that mean that I need to say something, but I don't know how to say it. It's more like some form of noise has been added,
Mm-hmm.
and so we are seeing that in the graph that we have now. Is that
Yes,
like we've added?
yes. There's there's variability now,
Yes.
but it's only coming from the uncertainty in the timing of events. That's the key thing. The rates are still the same. So this variability is a function of the discrete nature of the population and the variation in the time and order in which births and deaths happen.
I'm asking that because like when we started, you mentioned that the stochastic models are characterized by fluctuations
Mm-hmm.
and noise.
Yes.
So like it's
Yeah. So here we clearly have it's following the same deterministic skeleton, as we might say, but then overlaid on that there is variation and fluctuations, which is only a feature of the stochastic model. Okay? All right. Okay, so I've introduced the stochastic population models and the stochastic simulation algorithm, continuous time Markov processes. Well, hopefully we haven't really seen this, but in the large population limit, dynamics of the stochastic model will tend towards the deterministic model. We've sort of seen that, but we'll come back to that in the next lecture. And it suggests that there's a relationship between the deterministic model and the ensemble average of the stochastic model. So far, it seems almost exact, but we'll explore how exact and how limited that is in the next lecture. Okay, I think we should stop there. I've got a few other slides, just looking at some more exotic models and some interesting things, but they're not essential. So I suggest we have a couple of minutes break and then start at 5 minutes past 12 for the next lecture and get into the epidemic models. Okay. in the interests of time, we should probably get cracking. First few lectures are a bit of a recap, so it will help as people drift back in. So in the last lecture, we introduced this idea that the discrete nature of populations is a bit insane for description by a deterministic model, because if we have an infectious disease where our infectious individual is slowly recovering until they have a tiny little bill of a duck that is still madly transmitting disease in our population, that's not very realistic, because in reality there's a pretty good chance that a single individual in a population could recover before they transmit the disease, with the chance depending on the type of the disease. Those details, those sort of effects, though, we wouldn't expect to matter in a large population, because when you've got a lot of infectives, then whether or not you've got a small fraction of a duck or not is going to make very little difference. Yeah? And that's why in a large population, deterministic differential equations can be such a good description of disease dynamics. The fractional change just doesn't matter. Okay? On the flip side, we would expect that stochastic effects must be much more important in small populations, or when incidence is low. Okay? So let's start to explore these ideas of what a large and small population effect has on epidemic dynamics by looking at some simple stochastic epidemic models. Okay? So, simplest place we can start is the SI model. Okay? We have two compartments, fixed population size equal to the sum of the susceptibles and infectives, and a single event that can happen. Okay? One difference here is that the event corresponds to a change in two state variables. So we didn't see that in the last lecture, but there's no reason that we can't do that. So we have a rate that susceptibles go to susceptibles minus 1, infectives go to infectives plus 1. Okay? And we're going to assume frequency dependent, well-mixed population. So our transmission rate happens at the same rate as we had before in the deterministic SI model. So the deterministic formulation would be these familiar differential equations now, and we know, or if we don't know, we will maybe see it in the later practicals, that this is one of the few examples where we can get an exact solution. In fact, it's the same solution as we get for the logistic model. Okay. We introduced the Gillespie algorithm, which we can use to simulate any epidemic model, and in fact, we could just implement and adapt that code to simulate the models in this lecture and in the practicals. It takes a bit of time, so just to save us some time and to give you some skills which are maybe more translatable to building your own models and doing some more real-world work, we're going to do this using one of the packages in R that's been developed to quickly write stochastic models. So SimInf is, according to its press, a package which provides an efficient and very flexible framework to conduct data-driven epidemiological modeling. It's more or less true. It is certainly a very efficient way to simulate simple stochastic epidemic models. A nice thing about it is it's been designed to simulate metapopulation models, so you can have multiple different populations. It's got a very high-level R interface in order to define the model. It uses the exact Gillespie algorithm, but it also has this flexibility that it can model births, deaths, and movements between the patches as pre-scheduled events. So it was developed for looking at animal pathogens in particular, where you might actually know when the animal movements are happening and might want to replay that. You can use it for lots of different things. It is quite flexible. The most important thing, and the reason actually for using it rather than writing your own Gillespie algorithm in R code, is that it is much, much faster than standard R code. It takes your model and it compiles it into what's called C++ code. If you know what that is, you'll know that that means it's very fast. If you don't know what that is, it doesn't matter. You just need to know it makes it very fast. Okay? And it saves you a lot of pain learning C and C++, which I love, but most people could do without. It's fast. Okay. As with learning how to use DE-solve, though, there is a cost of entry here. We need to give the package, the functions in the package, the information to say, this is the model that I want to simulate, and this is what we want to see. Okay? So this is the R code that we need to simulate the SI model. Okay? So it's a bit chunky, but it's still a lot less than we saw for the functions that I wrote by hand in the last lecture. So what do we need to tell it? Well, first of all, it needs to know the number of states in our model and the initial values of those state variables. Okay, so that makes sense. And it expects this to be a data frame, which is named. So here we've got an S compartment with 499 susceptibles and an I compartment with 1 infectious individual. It needs a separate list which names these compartments in the same order. So here we have S and I, and it needs a definition of all of the events that can happen in the model. Okay? And it expects this using a notation which is quite common in stochastic modeling, but maybe looks a little bit odd. So we have an S on this side, so this is the compartment that is changing or that is losing an individual. Okay? And at this end, we have the infectious individuals. So what we're saying is that the only event that happens is a susceptible moves to the infected compartment, and it happens at this rate, beta times SI over N, but I've written it as S plus I, just because we haven't got an N in the model. We could have an N, which just doesn't change, but yeah, it's just easier to do it this way. Then we need to say over what time do we want to get output from the model, just like DE-solve. And then we pass this information into a function called mparse. Okay? There are actually some pre-coded epidemic models in the SimInf package where you can just give the parameters and it will run an SIR model or different types of models. Mparse allows you to specify your own model, and that's why we're using this here, just to keep everything nice and general. Okay? So it expects the transitions, compartments. The G data is the initial value, the values of the parameters, yeah, which have to be named vectors using the same names as we defined the transitions. When we run this, it doesn't run the model. What it does is it makes an R object, it compiles it to make that fast code, which we can then use to run simulations of the model using the run method. Okay? And then it has some nice plot functions. Again, it's better over here, which will give you a nice plot to show the output of the model with a legend. So the susceptibles going down, the infectives going up. Okay? Not too bad. All right. If we want to run multiple realizations, replicates, we can make use of the fact that the package has been written to work with multiple patches. So rather than just running for one population, we make another variable n for the number of populations. So here, chosen 5. So the red code is the new bits that I've added here. Instead of specifying a single S compartment, we specify a vector of values. So this data frame now has 2 columns, S and I, with a row for each patch. Each patch is identical because we're doing a replicate. So we just repeat the initial conditions. We do exactly the same thing as before. And when we ask it to plot here, we're now asking just to plot the I compartment and to plot the individual replicates. Okay? So here we have the output now for 5 replicates from the SI model. Okay. immediate things, what can we say about this that are similar and different from the deterministic SI model and from the logistic model that we saw in the last lecture? Sorry? So again, we've got this variability, sort of delay, in terms of when we reach full saturation of the population. So everyone becomes infected. It takes a different time in each.
Do we have a set carrying capacity here?
Yeah, because we've got 500 individuals that can get infected. Well, it can't
It doesn't exceed the
because of conservation of people. So the deterministic solution, the SI model, is the same as the logistic model, but the stochastic model is different because it can't exceed the fixed size of the population. Okay? Yeah, good. What else? There's one other feature. So there's a lot of variation here at the beginning when the numbers are small, which leads to this variation. But once the epidemic takes off, it's pretty much consistent across the during the epidemic phase. Okay, so once the numbers of infectives are high, everything looks a lot more like the deterministic model. The variation's only really coming in from this early period when the numbers are small. So we get a variable delay time at the start of the epidemic. Okay. So that suggests that in large populations, we don't need to worry about stochasticity. We can just use deterministic model. Okay. So what is the large population limit for the model, though? Okay. So here, we start with an initial number of infectives of 1. And here, we start with an initial number of infectives of 10. Okay. So the relevant large population limit for the SI model is the initial number of infectives that we have. So the more initial infectives, the less important stochasticity is. If we're only starting with 1 infective, though, we see a huge amount of variation, no matter the size of the host population. Okay? That's not actually going to make a difference. Okay. And, okay, we've got some, I've been very good here. I've done some R code where I've added a bit of transparency to the lines just to make this easier to see. Okay. There's a curious thing happening here, though. So again, as we saw with the logistic model, if we plotted over, and again, apologies, I should have done that. If we plotted over the deterministic solution, the stochastic epidemic curves are more likely to be late rather than early. Okay, that's kind of curious. That's not what we saw with the very simple linear growth models. And there's a very subtle reason for this. And we can show it, and I'm not going to try and do this proof, so don't worry, but we could show it by deriving what the average is of the stochastic model from first principles. Okay? In exactly the same way as I derived the Gillespie algorithm, we can write down equations called master equations for all of the events of our model, derive the probability distribution, and then calculate the average by integrating over the values of the state variables. Okay? You do a lot of maths, basically. But what it comes down to is you get, in the same way as we did for the proof in the last lecture, we get a differential equation for the average, or the expectation of I, with respect to t, which depends on the expectation of the product of S and I. Okay? In a linear growth model, this isn't a problem. So this, we just get the expectation of I, say, and we'd be able to solve that, and it's an exact or it becomes exactly the differential equation model. This, though, is not the same as this, because S and I are not conditionally independent. Okay? The expectation of S times I is not the same as the expectation of S times the expectation of I, because S and I are related to each other. They have a correlation between each other. Okay? You might be trusting me at this point. You might be thinking I'm blethering, and where is he? He's pulled something out of his hat there. sort of have. You might have been introduced to the definition of variance, depending on how in your first stats course you were taught how to calculate variance. One of the definitions looks at the square of the mean minus the mean of the squares, or I've got that round the wrong way probably, one of the others, yeah? Those are different quantities. So the expectation of the squares of a quantity is not the same as the expectation of the quantity squared, okay? We can, it turns out, it can be shown that we can write the covariance between S and I in terms of the expectation of SI and the product of the expectations of S and I. So we can rewrite our equation for the expectation, the differential equation for the expectation of I in terms of the terms of our deterministic equation, our familiar deterministic equation, plus this extra term, which is the correlation between S and I. Okay? Does that sort of make sense? So the deterministic differential equations are what we'd call in physics the mean field, in that it's the average behavior if we ignore these extra correlations between the variables of our model. Okay? So as long as this correlation is small, yeah, the deterministic model is going to be a good approximation to the true average. If there are any strong correlations between S and I, then we're going to bias our estimate of the average by ignoring the stochastic dynamics. Okay? Now in the SI model, we have a very strong negative correlation because the only state you can be in is either S or I. So as soon as you go to S to I, you have a negative correlation there in the values of S and I, which means the average of the stochastic model is less, has a slower rate than the deterministic model because of this correlation structure. In an SIR model, it's not quite as obvious, but there's a general principle here that the bigger the correlation between members of our population, and then the more misleading the deterministic model is going to be. So if you have heavily structured populations, particularly if you have diseases that are spread over networks, then that's why deterministic models are not a good way to simulate or to describe those types of epidemics, because they're going to drastically overestimate the rate of transmission due to the clustering in those populations. So network models are almost always stochastic models for that very reason. Okay. It's partly in the side, bit of broccoli, but it points to this deep relationship between the deterministic models and stochastic. The reason we introduced this type of stochastic model is because we have this relationship, and it means that in some limit we expect our stochastic behavior to behave like the deterministic model, which is another sanity check that our stochastic model is behaving the way it should, because we don't have otherwise we are just simulating a black box and we don't necessarily know that our model is behaving correctly. Okay. So, what does this mean for the stochastic SIR model? So we now have 3 state variables. We have 2 events. We have transmission, as before, but we now have recovery, which we're assuming happens at a constant rate, which I've written here in terms of the average infectious period. Okay? All right. Little bit of extra code. We need to add on the R compartment. Our transitions now becomes a list with an extra event. Okay? I goes to R at a rate 1 over Ti. I have to specify the extra argument, and SIMINF does all of the work for us, and we get a single stochastic replicate of the SIR model here. So, what if we look at this invasion scenario that we saw in the practicals for the deterministic model again? How does the stochastic model look different? Well, again, we have variable timing and size of the epidemic, as we'd expect, sort of clustering around the average of the deterministic model, but Again, we have something completely different, completely new here. Some epidemics are failing to take off completely. Okay? Stochastic model captures that probability of extinction. So if we look at the final size distribution, we get a bimodal distribution for these parameters that I've chosen. So the majority of outbreaks will have a final size which is clustered around that, which we would expect for the deterministic model. But we then have this other mode, which is those introductions which just lead to no outbreak. Okay? So already there's actually a really important insight here into the global transmission dynamics of some infectious diseases. So influenza has a relatively low R0. Okay? There's a lot going on with influenza, but because of the short infectious period and the low R0, it means there's a very high probability that when you introduce a case of influenza into an area, that person will just recover before passing it on and starting an outbreak in the community. So the influenza outbreaks that we do see around the world are not the result of single introductions, but likely due to multiple introductions of infection. And there's many hidden introductions that we are just completely missing. Okay, and that has important implications for the global dynamics and the spatial dynamics and spread of infections. Something we also saw with the SARS pandemic. Pandemic modelers love to make little animations of, oh, we introduce a case of disease and it spreads across the country in a wave, and it's wonderful and beautiful. In reality, when we looked at the genomic data in the UK and in other places, hundreds of introductions, all happening at the same time, multiple seeds, very little time to actually deal or respond to that. Okay. So stochastic dynamics, incredibly important, not just for understanding behavior in a local location, but for larger scale, national level and spatial dynamics of infection. Okay, I'm pulling this out of the hat again. We can show, using a completely different class of models, the probability of extinction is approximately 1 over R0. Okay, and that should make sense. The higher R0 is, the more likely an outbreak will start. The lower the value of R0, the higher the chance of extinction happening in the early phases of an outbreak. Okay, how am I doing for time? I'm not doing bad for time, actually. Okay, not bad. Okay, I want to talk now about this assumption that we've made about recovery happening at a constant rate. Okay, we've just implicitly done this because it's kind of easy. It's not very realistic, okay, and there's an important reason for that. If we have a constant rate of recovery, what that's saying is for an individual, okay, we can now think about individuals because we're in a stochastic model. For an individual, the time to recovery is going to be exponentially distributed. Okay, that's a very strong assumption. And it's one that isn't really backed up by empirical data for most infectious diseases. So this is some data and some examples showing comparisons of infectious period distributions for different models, motivated by measles. So the top left panel here is an empirical distribution of the estimated infectivity per day after infection. Okay, this was estimated using household data from the 1950s in England and Wales, where there were nice and large family sizes where you could actually count the number of infections and work out what the serial interval was. And what we see from observational studies of measles is that most individuals become infectious at the same time and have a very consistent latent period. Okay? Although we're indirectly measuring this. So this is an approximation of the curve of your probability of being infectious after being infected. Okay? If we compare that to what the probability of being infectious would be if we have exponential latent and infectious periods, be this gray curve here. Okay? And you see in comparison, there's many, many more people infectious immediately. and a much, much fatter tail of individuals who are infectious for much, much longer. Okay. Another common assumption we like to use in epidemic models, especially for measles, is we have a fixed latent and infectious period, and that would look like this. So we'd expect everyone to be infectious at the same time. That's not a great representation either. Somewhere in between, we need a distribution that's either more normally distributed or is somewhere in between. And the gamma distributed latent infectious periods are a convenient way of doing this. Okay? Katie's already talked about this and introduced this. Gamma distribution we've seen a few times now. Katie's mentioned it in this context. We've also seen it in the programming practical. It gives this flexibility with a shape parameter that allows us to modify the variability in the time that it takes for you to become infectious, as well as the average time. Okay. The shape parameter, and why we really love gamma distributions for epidemic modeling, is that it can help us to incorporate gamma distributions into a Markov stochastic model. Okay? So actually I skipped ahead of myself there. I should have said this first. The problem with this, which is inconvenient, is this is saying that the time, your probability of recovering, depends on your time from infection. Okay? Yeah? We didn't make the assumption of a constant recovery rate because it was realistic, because it was convenient, and we can simulate it easily using the Gillespie algorithm. Yeah? If the time is varying with time from infection, we can't simulate using the Gillespie algorithm. Yeah? We would either have to literally simulate this time for every individual in our population, so move from a compartmental model to an individual-based model, or we need to do something clever. And the gamma distribution allows us to do something clever because by splitting our infectious compartment into multiple subcompartments, but proportionately increasing the speed at which we move through each of those subcompartments, we can keep the same average time in the infectious compartment while reducing the variability that we spend in it. This is called the method of stages. And again, it can be shown that by chaining together these compartments, we get an infectious or a latent period distribution which has a very specific gamma distribution. But each individual movement is still a Markov event, which means we can simulate using the Gillespie algorithm. We don't need to use anything more exotic in order to deal with this. So, how would we actually go about doing this in a model? Well, rather than having a single eye compartment, we now have a rate at which individuals move into the first eye compartment. So I've labeled it I0 here for reasons relating to me preferring the C programming language, which counts from 0 rather than 1. But we could call this I1. So we have a rate of moving into the first compartment, which depends on the total number of individuals in all the infectious compartments, so the sum over all of the gamma stages. And then we have multiple events for all of those intermediate stages where ik goes to ik minus 1, ik plus 1 goes to ik plus 1 plus 1. Oh, that wasn't good. And you see the rate is now n over the infectious period rather than 1 over the infectious period. Okay? And then we need to take a little bit of care with the last infectious period. And it's all a bit fiddly, but it means that we can still simulate the model using the standard Gillespie method. So it's still more or less worth the effort. So, once you finish the course, you can look at my code and you can see how it works. We don't really have time to go through it in detail, but I've written some code which just makes this a bit easier, that just handles the bookkeeping of all of these variables. So I made a function which initializes the state with as many of these gamma stages that we want, so we can change the infectious and latent period distributions, and another function which just makes all of those intermediate stages for the model as well and sets it all up. Okay. There's nothing worse than someone talking through their code, so I'm not going to. Okay. Code's there. We can use it, and we can use it in the practical. There's a few things which we might want to have in a model which I've not talked about, which SimInf allows us to do. So we've only really talked about transitions of this form where A moves to B at some rate, okay, which has the effect A to A minus 1, B to B minus 1. We might, and I can't think of a reason we want to do this for epidemic models, but we might want reactant A to move into B and C at the same time. Actually, I can think of a reason. If we wanted to count the number of cases that we have, we might want to have a cumulative cases compartment, which we push in a case every time there's an infection event. That can be a useful little trick. So you have a single rate event which affects 2 compartments. Likewise, you can have 2 compartments then moving into 1 compartment. This is motivated by thinking of chemical reactions, I think, mostly. The really useful ones for adding in demography into an epidemic model, though, are modeling birth. So that's where something comes from nothing into a compartment, or death, where something goes from the compartment to nothing. And for that, we introduce this notation, which is the ampersand, and this represents the empty set. Okay, so essentially, we're going from nothingness to 1, or from 1 to nothingness. Okay? This is mostly for reference. What we want to do to wrap up the lecture today is to see what effect changing this the infectious period distribution has on the SIR model. Okay? So in these 2 side-by-sides, we've got exactly the same R0, okay, exactly the same average infectious period. The only thing that's changed is the number of stages, which by effect means the variability in the infectious period distribution. Okay? So for the standard exponential model, we have the very familiar SIR curve. For the gamma model, with a reduced variability, we see a strikingly different pattern of epidemics. Okay? We see a much higher rate of exponential growth at the beginning and a higher peak for the epidemic. Okay? Same number of people get infected, but the dynamics are very different. So the initial growth rate of the epidemic increases as the variability in the infectious period reduces, and also the variability between replicates decreases as you reduce that variability, as you might expect. Does that strike you as potentially worrying in terms of how you might want to apply if we were just working with a standard constant recovery model? What sort of issues could that give us if we're modeling real-life data, for example? Yeah? So this, potentially, if you ignore the infectious period distribution, and one of the ways, as we'll get introduced to by Thumby tomorrow, if we can estimate R0, is by looking at that initial exponential growth rate. Okay? And these simulations are illustrating the fact that that exponential growth rate depends not just on the average infectious period distribution, but how it's distributed as well. Okay? Those details really matter for getting that estimate of R0. So you could be you could dramatically overestimate the value of R0 and overestimate the amount of effort you need to control an infection if you haven't got that full detail about the infectious period distribution. Okay, so the 2 lectures in this session, we have introduced how to simulate stochastic population models, the relationship between the deterministic models we're more familiar with at this point in the course and the stochastic model. And we've started to explore when stochasticity matters, in particular for epidemic models. Fundamentally, it's when numbers are small, the beginning and at the end of an epidemic. That's when extinction is likely to happen and when stochastic dynamics will be more important. Also, though, when transmission rates are low. So there's some infections like measles, actually in a large population is going to be very deterministic. Other similar populations like whooping cough or lower transmission rate populations are going to be much more susceptible to demographic effects, even in large host populations. Probability of extinction is going to be related to R0, certainly in the initial stages of an infection. For later stages, it's going to depend on other factors like birth rates and the intrinsic dynamics. Don't really have time to get into that. More interesting thing happens for endemic infections. The other situation where stochastic dynamics really matter is when correlations are large. So when you have very clustered populations, either spatially or due to the nature of transmission of the infectious disease. So stochastic models, anything that's spread more in a network manner or a spatial manner, that rather than by purely aerosol transmission or casual contacts, stochastic effects are going to become much more important for describing and understanding both transmission and control of infectious disease.
So, I want to ask something.
Yes.
Is it just a number of these? Okay, so I'm just wondering. So what happens if, like, we know that this will matter if population is small. If population is large and the transmission rates say high.
Yeah.
So if, like, you have a balance of when this matters,
Mm-hmm.
what happens? Does it mean, depending on what I want, I could use?
You could use either. Yeah. So if you have a large population, you have high transmission rates, then, and you're thinking of a vaccination strategy for the next 5 to 10 years, deterministic model is probably fine, actually. And even for longer time periods, it's probably okay. But once you get to high levels of coverage and you're getting close to elimination, stochastic model is probably going to be more useful, but it depends on your question. Depends on your question. So, if you're thinking of the smallpox elimination, you think about looking at an individual country going down to elimination in the early stages of eradication, when there's still lots of inputs coming from other populations, the fact that you go locally extinct doesn't matter because you're constantly getting challenged from outside. If you're thinking of those very final stages where you're chasing down the final villages, families, literally, those contact networks, if you wanted to model that as a stochastic model, would be much more effective for looking at questions about contact tracing. And you'd ring vaccination, you wouldn't use a deterministic model. It wouldn't be appropriate. So it's very population dependent. These are guidelines. Even these guidelines can be wrong. So pertussis is a really interesting example. It's got the same R0 as measles in the UK, but the large population dynamics and the immediate response to vaccination were opposite to measles, and it was much more susceptible to noise because of the longer infectious period. Yeah, so it's very much a case-by-case basis. Okay. Any other questions? How are we feeling about stochastic models? Yep.
So I think I'm wondering, after this stochastic modeling, right, and when there's an ongoing outbreak, for example, how then do you determine which, maybe I assume that the relationship between each node here is collaborate or something. Where do you actually maximize the impact of your vaccine
So I'm going to answer that two ways. The first is, if we're talking about, major policy choices on vaccination, it's very rare we do any other targeting than maybe an age group or to make a disease, a vaccine available. If you wanted to target vaccination spatially to a particular region, there's optimal ways you could maybe do that, but there's ethical issues and practical issues with whether or not you would choose to vaccinate this community but not offer the vaccine to this community because you think there'd be an overall better benefit. That's quite a difficult ethical and practical question. Stochasticity can be important in terms of how ways you might get extra benefits from vaccination. So a really powerful example of this, but it's not something I'm aware any country has deliberately tried to do, is that you can show using models that if you have periodic outbreaks of a disease, like for measles, whooping cough, chickenpox, any of the classic childhood infectious diseases, if you use what's called pulse vaccination, so you introduce vaccination incredibly quickly with, say, a massive intervention campaign, and you synchronize all the epidemics in a region geographically, you will maximize the chance that you will increase the chance the disease gets eliminated immediately due to stochastic fade out. If you introduce your vaccine at different times in different regions, then you can actually enhance the persistence of the disease by putting all of the regional epidemics out of phase with each other. So you get more what are called rescue effects. Okay? So there's theoretical ways where stochasticity could be a really useful tool to push towards elimination faster by clever use in the timing of vaccines. In practice, I'm not aware of any situation where that's happened or been done. And for most vaccine decisions, those types of spatial dynamics aren't even figured in, actually. Katie, are you aware of any spatial models which are used?
Not really, just happen to see that we used just this method in academic setting, and I was wondering that would be useful if it can be implemented in practice.
Yeah. I think that there definitely are. There are things which, stochasticity and targeting can definitely enhance the path to elimination. I think the most important reason, though, for including stochasticity in a model used for vaccine policy is to improve the realism and to improve a measure of the uncertainty. So it's understanding the bounds, it's getting more realistic estimates of transmission rates and disease parameters from data, and also making more robust assessment of what the variation we would expect to see for a policy in a real population. I think that's the main reason for using stochastic models rather than deterministic models.
Thank you.
Okay, I think, well, no, we're late now, but it's time for lunch. So immediately after lunch, we'll be coming back in here for practical session again, so getting the chance to explore and play about with stochastic versions again of these simple epidemic models that we're now quite familiar with on the deterministic side. We'll now be looking at those from the stochastic session. Okay, thank you very much. Yes.
5 minutes for a few questions.
Absolutely.
I'm taking the talk tomorrow
Ah, okay.
on behalf
Wait a minute.
of
Let me just. Should switch myself off.
on annual estimation.